During the last lecture, we started describing the energy levels of organic molecules, and in particular, we gave some rules that are governing such energy levels. We have seen that this electronic spacing generally is much larger than the vibrational spacing, much larger than the rotational spacing, and much larger than the spin contributions, you remember. We introduced the absorption coefficient with the Lambert-Beer law, and we have shown that the absorption coefficient alpha is related to the extinction coefficient that we introduced in the previous lectures. We have seen that there are some selection rules that govern the transition between states, and in particular, there are three strong rules. That is, if you want to excite a molecule by means of light, the energy of the photons must be equal to the difference of the energies of the starting and arrival states. The parity of the two states must change from the starting to the arrival state, and the spin must be preserved, the total spin. So we have shown that you cannot have a transition that is driven by light from a singlet state to a so-called triplet state. And always keep in mind that a neutral molecule in a ground state is always in a triplet state. So the ground state is always a triplet. Then we have introduced this alpha coefficient, and we discussed about the dependency of the intensity of a beam that is absorbed in a medium. And we have introduced this absorption length. That is the inverse of the absorption coefficient, and we are given some hints about the absorption length. So this is the length that is that the light should propagate inside an absorbing medium before decreasing its intensity by a factor 1/E, where E is 2.71. And we have given some formulas that connect the let's say description of absorption in the physics vocabulary and chemists vocabulary. Physicists are describing absorption by using this formula, where they use the exponential function with a base E. The chemists describe transmission by means of an exponential function base 10. So there is an offset between the two representations. So we define the absorbance and the transmittance, and we introduced a molar extinction coefficient, epsilon. And we have seen that there is a relation between the absorbance of a medium and these three quantities. So the absorbance is the product of the molar extinction coefficient, the concentration of the molecules inside the volume, and the thickness of the sample. Okay? So if you have an absorbing material, say the wonderful colored glass of a window in a church, no? You have such wonderful glasses that are blue, green, red, and whatever. And you ask yourself, how strong is the absorbance of these windows? Then the absorbance is related to what? First of all, inside your glass, there must be molecules which are absorbing light. So the molar extinction coefficient must be different from 0. If the molecules do not absorb, the medium doesn't absorb. Okay? Then the concentration of the molecules inside the medium must be large if you want to have an absorbing medium. And the absorbance is proportional to concentration. So if you have many absorbing molecules per unit volume, your absorbance will be large. And finally, the thickness of your sample must be large. So the absorbance is proportional to the thickness. Clearly, if the thickness is 0, or the concentration of the absorbers is 0, or you have absorbers, but their molar extinction coefficient is 0, then the absorbance is 0. Now, consider that the concentration is independent on frequency. The thickness is independent on frequency. These are quantities that do not depend on frequency, but the molar extinction coefficient does. So it might be that a certain frequency a material is absorbing and another frequency it is not absorbing because its molar extinction coefficient is frequency dependent. That is, we gave this example, living tissues, and we have shown that in the case of hemoglobin, hemoglobin has a strongly wavelength dependent extinction coefficient, so it can absorb light in a different way in the ultraviolet and blue regions. Okay, now we start from here. We finished discussing these slides with the previous slide, and we give just some element of Boltzmann statistics. Now, we should be careful because when we discuss of quantum systems, okay, the applicable statistics are not the Boltzmann statistics, but they are the Bose-Einstein and Fermi-Dirac statistics for bosons and fermions. Since that normally a molecule is at room temperature, so we are far from the absolute zero, far from temperature equal to 0, the statistical distribution of particles is well described by the classical Boltzmann model, because we know that quantum statistics converge to classical statistics for large temperature. Okay, so we do not discuss Fermi-Dirac and Bose-Einstein, and we just describe Boltzmann statistics. And what does the Boltzmann model say? It says the following. If you have a physical system that is characterized by several energy levels, you see here the levels here, so it can occupy several different energy levels with increasing energy. Here, for the sake of simplicity, the energy levels have the same spacing, so the spacing is constant, but it is not necessary. Okay? And then you ask yourself, what is the probability that my system is in the energy level at energy E? So what is the probability that my system is here, or here in the second level, or here in the third level, or here in the fourth level, and so on? Okay? Then you can show with this formula that is written here that the probability that your system has got energy E divided by the probability that your system has got energy E naught. What is E naught? Is the energy of the ground state, the lowest possible state in energy. So this ratio is proportional to the Boltzmann factor. So E to the minus delta E, that is the energy spacing, that is E minus E naught, the difference of the two energies, divided by the Boltzmann factor, KB times the temperature in Kelvin. Okay? This is what you have from Boltzmann statistics. So clearly, if the temperature is 0, at absolute 0, this factor here is infinite. E to the minus infinite is 0. And then the probability that you occupy any level at energy E different from the ground state is 0. So your system will be in the ground state at temperature equal to 0 Kelvin. Okay? If the temperature is not 0, there is a probability that you are in the first, second, third, fourth excited states. Okay? Now, if we have a set of molecules, okay, say capital N molecules in a container, and all these molecules are identical, and they are at the same temperature, and so they have the same energy levels, you ask yourself, what is the ratio between the number of molecules that have energy E and the number of molecules that have energy E naught? Okay, so we are not speaking anymore of probabilities, but we are speaking of number of molecules. Okay, then you can show that you still have the Boltzmann factor, this E to the minus delta E divided by KB times the temperature. So the Boltzmann factor is the same here, but here you have a multiplying term, and this G that you have here is the degeneracy of your energy level. In atom physics, when you studied the hydrogen atom, for example, you discover that the energy of the 2s level is the same as the energy of the 2p levels. So at that energy, you do not have just one level, but you have four energy levels, the 1, the 2s, and the 3p orbitals. Okay? So each energy level of a system may be degenerate due to any symmetry of the system of the molecule. Now here, when you calculate this occupation number here, you have to multiply times the degeneracy of your energy level E divide by the degeneracy of the energy level E naught. Okay? What does it mean? Of course, that if, for example, the degeneracy of the first excited state is 1000, you will have 1000 more molecules in that state because there is more space. Okay? So normally you have to take into account this to be precise. Okay, now and this is the important thing that you have to understand. Okay, if you, for example, consider that these are electronic states, so states that are in which the electrons have a different cloud shape, we have seen that the electronic spacing is typically between 2 and 3 electron volts. So let's say 2.5 electron volts. Okay. Now, if you calculate the ratio of the probabilities to be in the first excited state divided the probability to be in the ground state, so the probability to be in the state E1 divided the probability to be in the state E naught, you have to calculate E to the minus the energy difference, that is 2.5 electron volts, divided the kBT. Okay? And I remind you that if you want to pass from electron volts to joule, you have to multiply by the charge of the electrons. So 2.5 electron volts is 2.5 times 1.6 10 to the minus 19. And you see that, therefore, At the numerator, you have something of the order of 10 to the minus 19. At the denominator, you have the Boltzmann constant, 10 to the minus 23. If you make the calculation, you see that this probability is 10 to the minus 42. So it's an incredibly small number. What does it mean? It means that when you have an organic molecule at room temperature, at 300 Kelvin here, the probability that the ratio of the probabilities to be in the first excited state and the ground state is 10 to the minus 42. So when you are at room temperature, where will it be, the molecule? In the ground electronic state. There is no chance that it is excited, okay? And if you excite it, it will go back very quickly, okay? So at room temperature, if you go back to the sketch that we made for the electronic levels at the very beginning, we said, okay, a molecule can be represented like this, where this is an electronic level. This is the first excited electronic level. These are vibrational spacings. Then the molecule must be in this group of levels here, okay? If you take, the spacing of the vibrational levels, with this spacing is around 0.12 electron volts. So it is more or less 20 times smaller. If you calculate the ratio of the probabilities, this ratio is of the order of 0.01. So it is 1%. Okay? That means that if you are at room temperature, all your molecule will be in the ground electronic states, and out of this, of 100 molecules, 99 of them will be in the ground vibrational state, so they will not vibrate, and 1 out of 100 will be in the first vibronic state, so it will vibrate, okay? And of course, if you want to know what is the probability to be in the second vibrational state, then the energy spacing is double and the probability is smaller. So there is almost no probability to be in the second vibrational state. Okay? If you take the rotational levels spacing, we told that every vibrational level can be split in rotational levels. Then this splitting is 5 × 10⁻⁴ electron volts, and the probability is 0.98. The ratio is 0.98, is 1. What does it mean? That when you are at room temperature, the rotational levels can be occupied. So the molecule can easily rotate. Okay? So what we understand is that a room temperature, that is the temperature at which we operate normally in biology, because if you want to study tissues at cryogenic temperatures, you don't have any more living tissues, no? All the molecules that you use to stain or label the biological media, they are in the ground electronic and vibrational state. And possibly you can have rotational levels occupied. Okay? What does it mean? It means that if you have, for example, a solution, no, with a solvent, and inside the solvent you put molecules that are all identical, okay? They have a certain set of energy levels. You do expect that at room temperature, all the molecules are in the lowest possible electronic state and in the lowest possible vibrational state. Okay? Now, the so-called there is a notation from chemistry that the highest occupied molecular orbital, so in a molecule, you will have that there will be an electronic level that is occupied, and there will be a free electronic level above that is not occupied. This is the one molecule could be a molecule that has got the internal shells that are filled with electrons, okay, like in a heavy atom. And this is just the highest occupied molecular orbital. This is named the HOMO band in chemistry. So this is an electronic level that is composed of several different vibrational sublevels. Okay? And the first excited electronic state that you can reach with an optical transition is named the LUMO band. And this is the lowest unoccupied molecular orbital. Okay? So in chemistry, with molecules, you use this notation. You call the ground state S naught, that is a singlet state. That's the why I call it S. It's a singlet state, is named HOMO, and the first excited state that is a singlet state is named LUMO. Okay? Now, this notation is equivalent to the notation that you should have seen in your previous courses, that is the notation that is used in semiconductors. In semiconductors, the highest occupied band of levels is named the valence band. The first unoccupied energy band is named the conduction band. Okay? But there is a strong difference between semiconductors and molecules, because in a semiconductor, when an electron is promoted in the conduction band, it's free to move in the semiconductor and can contribute to the conductivity and to the optical properties. In a molecule, the electron is promoted to an excited state, the LUMO band, but it remains on top of the molecule. It cannot go anywhere else. Okay? Did you attend the course from Professor Mattiello? So you study the OLEDs. In organic light emitting diodes, you speak of HOMO and LUMO bands, and these are the bands in between which you have the fluorescence emission, okay, or electroluminescence. Very often in organic light emitting diodes, you are in an intermediate condition, because you have an organic material that is not constituted by isolated molecules, but these are strongly interacting with each other. So there is mobility of the electrons among the molecules. And often you speak of conduction and valence bands, even in organic materials. But be careful. In our case, these are really HOMO and LUMO bands. Okay? And always remember that the valence and conduction notation is only for crystalline semiconductors. To be correct in organic semiconductors, you should speak of HOMO and LUMO bands. Okay. So here in this figure that you see here, you have the absorbance, okay, that quantity that we discussed before, of a solution of a given molecule, oxazine, that is solved in 3-chloroethane. This is just an example. So you have a solution of molecules in an organic solvent. And you see here, this is the energy in electron volts. This is the energy of the photons that you send on top of your system. And you see, until when the energy of the photons is low, so below 1.75 electron volts, more or less, so photons of low energy. So these are photons that cannot reach the excited state. You don't measure any absorption. The absorbance is 0. There is no absorption. As soon as you reach a certain energy for this molecule, you see that the absorbance increases and there is a peak situated here. But if you look carefully at this absorption spectrum, you will see that there is another maximum here and there is another maximum here. So absorption is constituted by several peaks. And you see here there is a fitting with three green curves that correspond to 3 maxima. What is happening here? It is happening that at room temperature, a molecule is in the ground electronic state and in the ground vibrational state. And when it absorbs light, it can absorb light and go from the ground electronic state to the first excited electronic state, and could go to a level where the vibrational energy is 0. It doesn't acquire a vibration. But you can also have the second transition here, the transition from an electronic state that is the ground, vibrational state 0, and you finish here to a state where the electronic level is the first excited, and you have a quantum of vibration, okay? And you can also transit to the 3rd vibrational level or to the 4th vibrational level. And this transition corresponds to photons of increasing energy. You need more energy to make this transition. And you see it here. In the absorption spectrum, you see that your solution with molecules absorbs light at energy here corresponding, it's written here, let me, yes, 1.9 electron volts, 1.96 electron volts, and 2.08 electron volts. So you can absorb energy at several different energies, and this is due to a vibrational contribution. Now, you see from this figure that the absorbance corresponding to the first transition is different from the absorbance corresponding to the second transition, and difference from the absorbance corresponding to the 3rd transition. So, for example, the amplitudes of these green curves is different, okay? What does it mean? That in some sense, it is much more probable to have a transition from here, B equal to 0 to B prime equal to 0, than a transition to B equal to 0 to B prime equal to 1. And one should ask himself, why is there this difference? And we try to give an explanation. What is happening here? Okay. What did we say? And we go back to a previous slide. You remember when we discussed the bonds between homonuclear bioatomic molecules. We said that this energy level, that is a bonding level, okay, the energy of this level is described by the Morse curve. And here on the x-axis, you have the distance between the 2 nuclei of the homonuclear molecule. So there is an optimum distance, okay, where the molecule is stable, okay, and will stay, okay. If the molecule is in a condition where the 2 nuclei are closer, the energy of this level will be larger. If they are farther than the equilibrium distance, the energy again will be larger, and the molecule will tend to stay here, okay. So this curve is describing the electronic energy of this level here. Okay, that is distance dependent. Now, clearly, an organic molecule like this, it is not a homonuclear molecule. It is not a very simple molecule, but clearly in mind, we can keep the very simple model of the Morse curve, okay? Just to understand. But clearly, there is not only one nuclear distance here, but there are all nuclear distances between all atoms. But if we try to model this molecule here, we could spend years to model it, and probably we wouldn't understand much. So let's make a very rough approximation and think that each molecule is described by the Morse curve. Okay? So the ground state will be characterized by a Morse curve, and there will be a dependency on the internuclear separation. Clearly, this is an effective internuclear separation. It's something that we use as a model. And the first excited state is characterized by a second Morse curve. Okay? Now, what does it happen when you are with a molecule that is not excited at room temperature? It will be in this electronic level, and it will be in the first vibrational level here. Okay? And if you send light on this molecule, it can make a transition up to one of these excited levels. Okay? Now, and let's for the moment look only at the red arrows in this graph. We don't look at we don't pay attention to the green arrow here, that is the emission. Okay? Clearly, there is a 1% probability that you are in this state here. So it can be that some molecule from here makes the transition on top, but these are very few. Okay? Now, around the minimum, the Morse curve, that is, you have seen the shape of this Morse curve, can be approximated by a parabola. Okay? And if you have a parabolic dependency of the energy, it means that you are treating your system of two nuclei as an harmonic oscillator. Okay? Now, in quantum mechanics, when you have studied the harmonic oscillator, you have seen that the levels of the harmonic oscillator, there is a ground state which hasn't got energy zero. It has got 1/2 h bar omega. So there is a minimum energy that is different from zero. And then you have some excited states, and the spacing between the states is constant in the harmonic oscillator. It comes out that you have equispacing. Okay? And you have shown that in a harmonic oscillator, the wave functions are given by the Hermite polynomials. Are these things that you know? Yes. Now, these Hermite polynomials are sketched here. So, for example, here in the ground state, you are in the ground electronic state, and you are in the first possible vibrational state that is given by the H0 Hermite polynomial. That is, there is a maximum probability that you are in the middle and some probability that you are far from the equilibrium position. Is it clear for you? Then, if you go to the first excited vibrational level, you have the second Hermite potential, and of course, these are not wave functions, but they are square modulus of the wave function. These are probability densities. Okay, and it will be done like this. In the second vibrational level, it will be given by this, and so on and so on. Okay? Now, and of course, this is true also for the excited state. In the excited electronic state, you may have several different vibronic sublevels that are characterized by a certain function. Okay? Now, look at here. In this graph that you see here, the spacing of the levels is not the same. You see here, the spacing here is larger than here, larger than here. What is due to? It is due to the fact that the Morse curve is not a parabola. It is distorted with respect to a parabola. And this makes that the energy spacing becomes smaller and smaller and smaller and smaller. Okay? Then I will comment on this later on, maybe on the next slide. Yes, I will do it, because I have the slide. Then, when you describe absorption of a molecule, you make some approximation. First of all, the Morse curve can be approximated with harmonic oscillator. And so you make the approximation that these states are equispaced. Okay? The second approximation that you make is the following, the so-called Born-Oppenheimer approximation that you should know because you have used this when you studied the hydrogen atom. And what does it say? It says, look, the electrons are about 2,000 times lighter than the protons, and so they move much faster than the protons. Okay? In a molecule, the electrons move very fast and the nuclei tends to be very slow. What does it mean? It means that when you have a molecule that absorbs light and makes a transition from electronic level to another electronic level, what does it happen? The molecule changes the wave function for the electrons. So the electrons in the ground state are described by a certain cloud, okay? And when they go to the excited state, they are described by a different wave function. So the electrons move a lot, they change configuration. But this transition is so fast that during the transition, the nuclei do not move. So it is as if the backbone of your molecule is frozen when you change the electrons distribution. That means that when you pass from here to here, this transition is vertical. Why? Because you remember that this is the internuclear distance. The internuclear distance doesn't change, it keeps constant. Clearly, this internuclear separation we define for two atoms in a bimolecular molecule, biatomic molecule, but it means that all distances in a complicated molecule we keep constant. And you see here, this is written here, the electronic transitions take place without any change of the internuclear distance. And this is called the Franck Condon principle. Okay? Then the other thing that you assume is that at room temperature, only the lowest vibrational level of the ground electronic level is occupied. So only this level is occupied. This is not completely true because 1% can be here, but we neglect. Okay? So you are here. And now you ask yourself, why are these absorption contributions different? And this is explained here. Because when you make a transition from here to an upper level here, remember that when you calculate transitions between energy levels, you use, let me go back, this formula here. The probability to have a transition is the expected value of the dipole moment between the arrival and the departure states. Okay? So what is important, it is the superposition of the wave functions of the arrival and the departure state. It is important that these wave functions are superimposed. Now, look here. If you start I see that here you are writing. If you start from this level here, where the probability to have the molecule is maximum here, and you make a transition here, or the second level, or the third level, or the fourth level, and the transition is vertical, you see that you arrive here to a position, for example, where the probability to have the molecule is small. Here, if you look at the transition at first level, the probability to have the molecule here is large. Okay, so the transition probability from here to an excited level depends on the superposition of the two wave functions. And this superposition is different depending on the level where you arrive. As a result, and we go to the next slide. It's almost 70. As a result here, this is more clear as a figure. You see that if you make a transition from here to an excited level, here the superposition in this case that is marked with a blue line is good. But for example, the transition probability from this state to this state here, it's smaller because the two wave functions superpose less. As a result, if you look at the absorption is given by several different contributions that are at increasing energy, no? Because if you go from here to here, you have a certain energy. If you want to go here, you must have a larger energy, and so on, and so on, and so on. So you have different absorption peaks. And you see here that the transition 0 to 0, that is from here to here, is less intense than the transition from 0 to 2, from here to here. That's the why in the absorption spectrum, you see contributions that have got different intensities depending on the structure of the molecule, on its energy levels, okay? And here they are represented the 6 lines, okay? As a matter of fact, if you measure experimentally the absorption spectrum, you will never see something like this. A peak very narrow, and then a second peak very narrow, and then a third peak very narrow, and so on. What is the reason why? We told before. The reason is that when you have molecules in a solvent, for example, or in a solid matrix, for example, every molecule has a different environment around. So, for example, these spacings are not the same for different molecules. So you will have a broadening of these levels due to this inhomogeneity. The molecules can move, so you have Doppler shift. They can hit the walls of the container and so on. As a result, the real absorption spectrum that you measure is something like this, very broad, okay? And it is the average of all these contributions. And normally, it is so much broadened that you do not even feel that it is composed by narrow lines. Okay. Now, in the case that I have shown here, these contributions are quite narrow, so you can distinguish them, but in other cases you can't. Okay. That's the reason why you observe something like that with maybe a stronger peak here because this transition is more probable, and the peak here because the 0 to 5 transition is large also in probability. Is it clear? Okay. Now, this absorption line here, this is marked in black, in experimental matter physics, in spectroscopy, is named the zero phonon line. Why is it called the zero phonon line? Because in this transition, no vibration is involved. You start from the state where the vibration is 0 to the state where the vibration is 0. It's not really true that it is 0, because in quantum mechanics, you know that the lowest level of an harmonic oscillator is not 0, it's different from 0. Okay? Now, look. Here, you see that this energy spacing is constant. Okay? This difference is equal to this, because we have assumed that the energy spacing here is constant. But in reality, if you go very high in energy, it is not at all constant. And the more you approach the energy where the Morse potential on the right-hand side gets flat at infinity, the more these energy levels are close to each other. Exactly like in the hydrogen atom. The energy spacing in the hydrogen atom decreases more and more the more you approach the ionization energy. Okay? As a result, and you will tell me, but professor, and then why did you tell all these things? Of course, I will reply, you are right. The result is that normally, when you have a polyatomic molecule, this is composed of many atoms that are connected by bonds. They can vibrate along many directions, and there can be many vibration modes, stretching, bending, symmetric and asymmetric stretching, and so on. And normally they are in homogeneous environment, and therefore, if you sum up the response of all these molecules, for example, that are in a medium, they sum up and they form bands that have only slight changes of the absorption. You get some very broad absorption bands with some feature. Okay? It is usually very difficult, and I would say it is impossible, from an absorption measurement that has been carried out at room temperature to understand what is the energy levels of the molecule. It is impossible. Okay? Spectroscopists, if they want to study the energy levels of a molecule, normally they measure absorption of very rarefied gases. So you take the molecules, bring to the gas phase, decrease very much the concentration so that they do not interact, and then you measure the absorption spectrum of the isolated molecule. But this will never happen in what we shall show later on. Okay? Now, we stop here. We have 10 minutes rest, and then we give some examples. Are there any questions? No question. So we stop the recording and